All right, so we're going to look at the proper definition of continuity now. So let's state it. We have been talking about continuity, but it's been somewhat informal because we're talking about how a graph looks, if there's a break in the graph. There is some elements of informality about that, and we need to be precise in mathematics, so let's give a proper definition of what it means to be continuous. So f of x is continuous at x equals a if what? Well, this is it. The limit as x goes to a of f of x equals f of a. Now, I bet you when you read that, it doesn't really tell you too much if you're not used to this kind of stuff. Whereas the previous discussion probably made a lot of sense, right? But when we do actual problems in calculus, this is the definition of continuity we have to use. If the teacher asks you if something is continuous and then you say, well, there's no break in the graph, it's not very precise and you could face losing some marks. If you're asked to prove something is continuous, you need to use this definition right here. And notice it involves limits, right? So this definition has lots of stuff hidden in it that it's not obvious when you first look at it, okay? The first thing to know is that implicitly, in other words, we're not even saying it, but it's assumed to be true. So I think it's necessary that we bring it out and say exactly what it is. Implicitly, we are assuming two things. First of all, we're assuming that f of a is defined, right? We couldn't even write this statement if f of a wasn't even a number. How can we write an equal between two quantities if this f of a doesn't even exist, right? So when we write this statement down here, it's implicitly assumed, it's like automatically assumed that a is in the domain of f, right? F of a is defined. And similarly, the second thing is this limit here has to exist as a finite number. That's not said either, but it's implicitly assumed. Since I usually find that most textbooks just say that and then expect students to be perfectly fine with it, but there's these hidden things that are assumed, which I think it's worthwhile to explicitly mention. So this limit on the left-hand side there, this limit must exist as a finite number. So f of a is some number, the value of this limit is some number, and if it so happens that those two quantities are equal, that's what it means to be continuous at x equals a. Well, that's fine. The way I sometimes like to remember it is this. Let's remember that when we did limits, I emphasized that so when we did limits, we saw that this limit does not necessarily equal f of a, right? They could be equal to each other. In other words, how do you do the limit? A lot of students think when they first learn limits, all they have to do is take that number a and just put it in there and work it out and you're done. In other words, they think that to do this limit, all they got to do is figure out what f of a is. In other words, they think these are equal. But that doesn't have to be true all the time, right? Sometimes they are equal and sometimes they're not. When they are equal, that's quite special, actually. So if you can do a limit by just putting the number inside the function and getting the answer f of a, and that's the answer for the limit, that's a special circumstance. And it's so special, in fact, that we give it a name. And that's exactly what continuity means, right? What does it mean for continuity? This limit is equal to the value of the function at that a. So if you can do this limit simply by putting the number a in the function and getting the f of a as your limit value, that's what it means to be continuous. All right, so let's do some examples here. You know, when we did, remember this theorem on polynomials? Limits of polynomials. Remember we saw that. How do we do the limit of a polynomial? Well, why don't we take p of x to be a polynomial? Then for any real number a, because remember the domain of a polynomial is all real numbers, we know that the limit as x goes to a of p of x. How do we do the limit of a polynomial again? All we got to do is put the number in the polynomial, right? We've seen this theorem before. And now we actually have a name for this now. This limit as x goes to a of the p of x, since we can do that limit simply by putting the number a inside the function and working it out, all polynomials, that's what it means to be continuous, right? So therefore all polynomials are continuous. At every value of a. You know, this is not surprising because how do polynomials look, right? Remember polynomials, they look kind of like this, right? They're kind of like, depends on the degree of the polynomial. But that's basically how they look, right? And notice this function is defined for all real numbers. And there's no breaks in the graph at all. It's a very smooth function. So that means all polynomials are continuous at every number. So let's say somebody asked you this question. Is f of x equal to x squared, say, continuous at x equals 3? Well, do you remember the graph of f of x equals x squared? I hope so. It looks like this, right? Let me try to draw that a little bit better. Yeah, good enough. And this is I guess if we look at our informal definition that we talked about before, notice this graph is at, let's say 3 is right here, right? Can I ask you what this y value would be? I hope you know it's 9, right? Because 3 squared is 9. Is this function continuous here? Well, using our informal definition, the function's defined there and there's no breaks in the graph. So yeah, it is. If we use the fact that, but what I'm trying to make this point is, if this was your question, you would say, the answer, if you wrote this for an answer, there are no breaks in the graph at x equals 3. So yes, it is continuous there. Is that a good answer? It's not bad, but it's not as good as it could be. This concept of not having to lift your pen from the paper, there's no breaks in the graph, this is an informal notion to help us understand stuff. But the real way we should do it is like this. The answer, the best way to give it would be like this. I would say that by the theorem of limits of polynomials, we know that, how do we do the limit as x goes to 3 of x squared? Well, by the theorem of the limits on polynomials, all we have to do is put the 3 inside there. And that gives us 9. And therefore, the limit as x goes to 3 of f of x is x squared, right, is equal to f of 3. So yes, it is continuous at x equals 3. Kind of a lot of writing, but that's really the mindset you should be going through, is that we evaluate the limit of the function at the number. How do we evaluate it? We use one of our limit theorems or one of our limit laws that tells us when we have a polynomial, we just put the number in and we get 9. And that's the same thing as f of 3, right? And x squared is f of x. And so look what we have here. This right here is precisely the definition of continuity, right? Now, I bet you don't like all this extra work. It was much nicer when we just had to think if there's any breaks in the graph and stuff like that. But this is really the proper way to do it, and that's kind of the way we have to do things.